In this video, I will show how to go through an epsilon delta proof of a limit in the form limit as x approaches a of some function is equal to L. And for the purpose of this video, I will be using this as an example. This is going to be different for when delta is only equal to one set value of epsilon, because I think that is a bit too easy to requisite an explanation. First thing we start off with is our definition of this limit. First, start with our want to show. Now we will write the definition of this limit. If you're unfamiliar with this definition and why and how I got to this definition, then you have a lot more reviewing to do before you can step into the Thunderdome of epsilon delta proofs, because this is probably the easiest part of an epsilon delta proof. Okay, now let's start off with the structure of our proof. Of course, we want to start by fixing epsilon as any arbitrary number greater than 0. This takes care of this. Now we want to take an epsilon, which we do not know yet, and then we want to prove this condition. So we start off with saying, and there's a hidden quantifier here where it means for every x in the reals. So we have to make sure that we specify and define x, or else you will be docked marks. Let x an element of reals, and now we assume the first part of our condition. Because if we can assume the first part of our condition and prove that the second condition is always true, then we have proven our statement. So we say assume 0 is less than x minus 1, which is less than delta. And now we prove this statement. And I won't write that just yet. This is the structure of our proof. And the most difficult part of this is obviously taking our delta, choosing our delta. What the heck is delta going to be? And a good way to start is first by doing the rough work. And a good way to start is just by trying to algebraically manipulate the conclusion into something that's a bit more familiar in terms of either our assumption or something else we know about limits. So let's see what we can do. Let's multiply 1 by x plus 2 so that we get this. And we know this is equal to this whole thing under x plus 2. If x plus 2, the x's cancel because this is minus, and we end up with minus 1. So this ends up being our algebraically manipulated solution. Now we can get x plus 1, x minus 1, because this, we just factor this one out, over x plus 2. Okay, and now let's see anything we have in common with our assumption here. We can see that x minus 1 has to be less than delta, or at least we're assuming that. And we have an x minus 1 here. So we can do this pretty simply. We can take out the x minus 1, and we're left with x plus 1 and 1 over the absolute value of x plus 2. And we know this must be less than delta. So we end up with this. Now this is the most important place. You should be able to understand every single step I did thus far. If you do not, then you have a lot more reviewing to do. This statement simply says that we can assume that x minus 1 is less than delta. This is part of our assume statement. We don't need to prove this, because we just need to prove that if this is true, then the conclusion must be true. So we don't actually have to prove our assumed statements. So now we have to find a delta that works. And this is where things get a little complicated, because it seems very unintuitive that you can just choose a delta value out of random, but that's essentially what we're doing. It's not exactly random, we just want to choose some small number. The smaller the number, the better, but most times 1 works. So let's say delta is less than or equal to 1. Then we know that this statement must hold true. This is probably the most confusing part of the proof, and I will explain later on why we can do this and why sometimes it might not work. Because, of course, we're just choosing at random. If we chose 100, chances are this isn't going to work because 100 is a very big number, but 1 is a relatively small number. So we can just choose 1. And now let's assume this statement. Now we can algebraically manipulate this statement to try to get it into terms of what we want. So first we want x plus 1. This is pretty simple. If we remove the absolute value from both sides, and then we add 2 to both sides, we get 1 is less than x plus 2, which is less than 3. And of course, if we take the absolute value of this is all less than 3. So we know that x plus 1, if we assume that delta is less than or equal to 1, then we know that x plus 1 is less than 3. This is very important. And now let's do the same thing for 1 over x plus 2. Sorry, I just realized this is not supposed to be plus 1. This is supposed to be, plus 2 is supposed to be plus 1. Now I'm going to do x plus 2. So let's skip this step and take this statement over here. And let's add 1 to every side. 2 is less than x plus 2, which is less than 4. Now, if we take the reciprocal, we know that 1/2 must be greater than 1 over x plus 2, which is less than 1 over 4. This is the reciprocal property. If you don't know this, try to review this. We have to switch the signs around. This is the reciprocal property. And now we know this is true, right? So we know that 1 over x plus 2 is less than 1/2. This is all assuming we derived all of these by assuming that delta is less than or equal to 1. Would you agree that if delta was less than 1, then these statements would still hold true, right? Because this statement will still hold true if if it's all like, let's say everything x minus 1 is less than 0.5. This implies that x minus 1 is also less than 1. Would you agree? These two, the first part of this implies the other. This is very key to understanding why epsilon delta proofs work, and especially why we can just choose a delta. If you do not understand this, try to convince yourself that it works. This means that for any delta that's less than or equal to 1, we know this must be true. And this is the thing that we use in these sorts of epsilon delta proofs. What we do is we set epsilon or a delta as the minimum of some values. And because we're assuming that delta is less than or equal to 1, we must put 1 into this value. Because the minimum function means, let's say we have like n here. The minimum function means that, okay, if 1 is less than n, then we choose 1 as delta. But if n is less than 1, then we choose n as delta. So either way, delta has to be less than or equal to 1, right? Because if n is greater than 1, then it'll just choose delta. And then this statement still holds true. So as long as we choose delta as the minimum of 1 and some other number, then we know that these two statements must be true. And would you agree that that means delta times x plus 1, the absolute value of x plus 1, times 1 over the absolute value of x plus 2 must be less than 3 times 1/2 times delta. In other words, 3 over 2 delta. This should make sense. Now, this is the final step of our rough work. We now, here, I'll move this down because this is a little squished over here. Now we need to find some delta such that we can finally get to our conclusion with epsilon. Because we're not trying to prove this is less than some value of delta. We don't care. We are supposed to find delta. We have to find that this is less than epsilon in some way. So what value of delta can we choose to make this all equal to epsilon, or less than or equal to epsilon. For the purposes of this, it's probably easier just to make it equal to epsilon. And we can very clearly see that if we make delta less than or equal to 2 epsilon over 3, then once we plug this in, we know that 3 over 2 delta must be less than or equal to 3 over 2 times, and then we plug this in, right? 2 epsilon over 3. And we see this is just equal to epsilon. So now we've proven this, right? And that means we've proven that delta times the absolute value of x plus 1 times the reciprocal of x plus 2 is all less than epsilon. And we know this is all greater than our original statement here, right? Which we can finally see it's equal to our conclusion. So we've seen that with our rough work, we have proven this. But wait, there's a gap in our understanding here. If there's not, then that's really impressive. But if there is, this is why. We have 2 values of delta here. How the hell can this work, right? How can we just have 2 values of delta? But like I said, we're taking the minimum value of 1 and some other value. And we found this other value as 2 epsilon over 3. So we can replace n with 2 epsilon over 3. And now I will explain why this works. We've shown that when delta is less than or equal to 1, we know these statements are true. So if 2 epsilon over 3 is greater than 1, because epsilon is arbitrary, right? Epsilon could be a million, right? Even if epsilon is a million, we're still taking 1 as the value. And if we know that 1 is the minimum value, is the value we know, then we know this is true. We know delta is less than or equal to 1. In this case, it's literally just 1. Which means we know this is also true. And because we've algebraically manipulated our statement to eventually get to, where is it? Get to this statement right here, right? By assuming that delta is less, well, in this case, equal to 1, then we know all of this must be less than 3 over 2 times delta. And because we can also choose delta as 2 epsilon over 3, then we see this is all less than or equal to epsilon. But you might be saying, but wait a minute, but we just said delta is equal to 1. So how can delta also be less than or equal to 2 epsilon over 3? It's a very good question, but that's the beauty of the minimum function. Because we chose 1, we know that 1 is less than or equal to 2 epsilon over 3. Would you agree? And would you also agree, if we would look back here, right? We know this is true. Would you also agree that if this is true, that means our conclusion, yeah, I'll just copy and paste this to make it very clear. Is all less than 1. Because we know that delta is equal to 1. This is this is all the case when 2 epsilon over 3 is greater than 1. And this means that this is all less than all less than epsilon as well, because epsilon is so much greater than 1. Because we know this is true, this also implies it's less than epsilon. That's why this works. And on the flip side, if that doesn't make sense, try to go back, try to understand it. It's a very, very key point in understanding epsilon delta proofs. And on the flip side, if 2 epsilon over 3 is less than 1, then we know this statement still holds true, because we'll just choose 2 epsilon over 3 as our epsilon value, or as our delta value. So no matter what, by setting this as a minimum and having 1 as one of them, we know this statement is always true. Always. That's why we take the minimum. And now we can finally write our final proof. We can start with our conclusion, right? Or sorry, not start with our conclusion. Let's start with this final. We're trying to prove that this statement in here is all less than epsilon, right? So let's just start with the first part of the statement, which is x is squared plus x plus 1 over x plus 2 minus 1. And obviously we know this is algebraically equal to x squared minus 1 over x plus 2, which we know this is equal to x minus 1, or x plus 1 times x minus 1 times 1 over an absolute value of x plus 2. It might help the reader if you, as part of this, to say thus. This isn't necessary. This is not necessary in any way whatsoever, but we can just say thus this is true, which means, and then we can say that x plus 1 is less than 3, and 1 over x plus 2 is less than 1 over 2. This is pretty optional because it should show in your rough work anyway, so they just check your rough work, see what happened. But this is just, I think it's a good practice to include it. I don't know what the TAs think, but I don't know. I think it's a good idea to put. So we know this lesson here. That's right, less than, right? That's less than 1/2. And we know this is less than our delta, and we can choose any delta here. Like we can choose either 1 or 2 epsilon over 3, and obviously we can only get to our answer if we choose epsilon over 3, 2 epsilon over 3. So let's put 2 epsilon over 3, and we know this is all less. Sorry, this is the wrong way. This is less than 3. This is less than 1/2, and we see that this is equal to epsilon. Therefore, we have proven our conclusion, and that is the end of the proof. I will say this part might be the most confusing, but as long as you realize that if we've proven this is true for less than some value, if we choose a value that's less than this, then this statement is still true. I think that's the main reason why epsilon delta proofs are so difficult to understand, because it doesn't sound very intuitive until you really dive deep into the logic. This is how epsilon delta proofs work. This is a very simple epsilon delta proof. In the future, I will be making videos on proving when the limits. Remember, this is what I like to call the vanilla epsilon delta proof, which is this is just as x approaches a of some function is equal to L. This is one of the easiest epsilon delta proofs you can do. So this is like the first stepping stone that you need to really understand before you tackle anything bigger. Later on, I will prove as x approaches a, f of x might approach infinity or does not exist, right? Which are significantly more difficult, or maybe even negative infinity. Also, when x approaches infinity, which is also quite difficult, right? Or this could equal L, this could also equal infinity, this could also be does not exist. There's there's a lot of different possibilities for what limit questions they can give you. I know on the midterm, I think the format was, if I remember correctly, it was the limit as x approaches infinity of some function is equal to, let me try to remember. I think it was equal to some value L. I think this was the format they gave on the midterm, and I know a lot of people didn't even finish that proof. So it's very important to understand the basics of an epsilon delta proof before jumping into the more grander and more difficult ones. If you can understand this, you're in good shape to move on.